Hello everyone, today we as group 17 from chemical engineering major, we would like to present our math assignment. And in this, my name is Raina Patriot, and this assignment consists two questions, and I would like to explain question 1 and our solution. So this problem involves determining the dimensions of supply box that minimizes the amount of material used. So this is an optimization problem. So we should use differentiation to find dimensions that result the least surface area while satisfying the volume constraint. And we have surface area, and the surface area of the box includes top area, bottom area, and vertical wall area. Since it's square box, our height and width should be equal. So first we write the area and then area equation, and then we write the volume constraint, and we are given the volume, which is 0.5 meter cubic. Then we substitute the height into the surface area formula, and after that we try to minimize A using differentiation, which means differentiate area with respect to x, and we can find x and then we find critical points, and after that we can find our x value. And then after this x value is equal to our width and length, and after that we can find our height using the volume formula and substitute our x value into into volume formula and find our height. So finally we have all our dimensions: height, width, and length.
Hello everyone, this is Wijaya Catherine, CME24099090, and I will be discussing the first part of the second question to the math assignment. Now, the second question asks us to calculate the total hydrostatic force that is acting on all vertical walls of the box when the base of the box is at depth of 5 meters submerged in normal fresh water. Now, we are given the information that the density of fresh water at 25 degrees Celsius is 1,000 kilogram per meter cube. Now, before we get into actually solving the question, calculating the fluid force of a vertical surface is quite complicated because of the depth, which makes the pressure not evenly constant across all areas of the box, as in the vertical surface of the box. And so to solve it, we would need integrals, specifically the equation of fluid force on a vertical surface, which will be times 4 later to account for all areas, all sides of the box. The specific equation for fluid force on a vertical surface is F as fluid force, which is equal to the integral of fluid density times the distance from the surface to point X of the box, which will be explained later, times the width of the box from point A to B. Now, to use this equation will require a little bit of imagining, and so let's see. For example, we have our box, and this is the surface of the water. The box is submerged 5 meters below the surface of the water. And so we can set our y-axis and our x-axis like this, where the y-axis is the same as the surface of the water, and the x-axis is the distance from that surface downwards, where the positive direction is down. We can set our point A and B as the top of the box and the bottom of the box respectively, and we can also plot in the dimensions that we found from question 1. And based on this information, we can deduce that the distance from the surface of the water to the top of the box is around 4.2063 meters. And that hx that we have earlier, which is we can plot the point x as somewhere in the middle of the box, and the distance from the surface of the water to that point x is what we would be putting as hx. And so next is the fluid density. Now, we were given that the density of fresh water is 1,000 kilograms over meter cube, but we would need it in Newton per meter cube, and so we would have to multiply it with the gravitational acceleration, which is 9.80665 Newton per kilogram, which we will be getting 9,806.65 Newton per meter cube. And we have the point A as 4.2063 meters, point B as 5 meters, hx, as we said earlier, as x, and the width of the box as, of course, 0.7937 meters. Now, from this point on would be quite simple, as we would simply be placing all the values correctly into the equation, which, if we time everything together, we will get 7,783.5381x from 4.206325. And so, if we integrate it, it will look something like this. And so, we would simply just be plotting 5 into the x squared minus 4.2063 into the x squared also. And so we would get 7,783.5381 times 25 minus 17.693 divided by 2. We will get the value of 28,437.15645 Newton. And considering that there are 4 sides of the box, we would simply need to multiply that answer with 4, which will then get the final value of the fluid force on the box as 113,748.6258 Newton.
Hello everyone, my name is Mark Desio, CME 2409068. Today I'm going to discuss the second part of question number 2, which involves a box submerged in muddy fresh water. This part is actually quite similar to the previous one, where the box was submerged in fresh water. The only differences are the depth of the box, which is 7 meters, and the density of the water. First, we should sketch a box and place it in a Cartesian field. Then, we can label the sketch with point A and B. Both the length and the depth of the box are 0.7937 meters. To determine the value between the water surface and the top of the box, we subtract the depth of the box, 0.7937 meters from 7 meters, resulting in 6.2063 meters. We label this unknown value as x, just like in the previous part. And when the sketch is complete, we can proceed to the calculations. Before continuing, let us write down the known values. For the density or rho, which is 1078.5 kg per meter cube, and when multiplied by the acceleration due to gravity, 9.8 meter per second square, we obtain the specific weight of the fluid, which is 10,576.472 Newton per meter cube. And the value of A is 6.2063 meter. The value of B is 7 meter. And the height we don't know, so we can just put the x like the previous one. And the width is 0.7937 meter. Next, we can calculate the hydrostatic force acting on the system using integral from 6.2063 to the 7, and we can put all the values here. The rho times gravity times the width and times the height. And after performing all the calculations, we find the value for one side of the box to be 43994.9751 Newton. Since there are 4 sides, we multiply this value by 4 to obtain 175,979.9003 Newton. So that concludes the discussion for question number 1 and question number 2, and thank you.